you, everybody who is watching this video? I would like to welcome into the fantastic program. My name is Olenjolai from Tanzania, or we call it United Republic of Tanzania, but simply can call it Tanzania in East Africa, in African continent. And I would like to present to you, or I'm ready to present, to share to you about the solutions that I'll be sharing to you, which I'm solving the complex national and even international problems in learning. So go along our YouTube channel called TANZANIA Online A-Level Secondary Schools, and the subject, the advanced chemistry, then the topic is general chemistry. And today we are going to cover the last two parts of the advanced electronic configuration. And this material is the class is for the Form 5, Form 6, and ODs. And this is the phone number, as I used to tell you, that in case you feel that you want to offer the Thanksgiving, you may do that. And this is lecture 18. Hopefully, concerning about the concepts of atomic structure, this will be the last one. However, I can make you some answer lectures, but just for the question solving, maybe from the final exam questions of atomic structure. But if just you manage to watch all the 18 videos or lectures, well, I believe that you know more than what you should know in general chemistry. So I would like to welcome you. So welcome into this part of quick review of what of lecture 7. Lecture 7, we covered about almost 4 concepts. The first concept we covered, I told you about valence shell, term that we call valence shell. We said that this is the outermost shell. And then we discussed about valence electrons. So valence electrons, these are electrons located or filled in the outermost shell. And I related the advanced electronic configurations with your ordinary or O-level electronic configuration. Then I told you about core shells, and these core shells, something we call them we call them noble gas sorting, noble gas shells. And then I told you about core or noble gas sorting, noble gas electrons. The term core, I told you that is similar to say inner. So inner shells. So for example, if you review the atomic structure during the O-level education, I told you that suppose that this is the first shell, we use though that this is the second shell, and this is the nucleus of an atom. So possibly we have 2 electrons, the first shell used to occupy 2 electrons, and then possibly we have here 1 electron, that this electronic configurations or electronic structure 40 this year. So this is what we call the valence shell, valence electron. Inner core shell, core electrons. And this is the nucleus of an atom. So we have been discussing and relating with how we can write electronic configurations of first electrons, we stay first electrons or fifth electrons. And I left the homework for you to do. I think that you've done. In case that you did, make sure to submit your homework on the comment sections to show me whether you succeeded or not. And even if there is any necessity for me to do correction for the homework or not. Because possibly some of the homeworks are very simple. They are straightforward. So today, let us start at this point. I would like to teach you the second from the last concept in atomic structure. The concept we call electronic configuration. Electronic configuration. Electronic configuration of atoms. In excited state. Electronic configurations of atoms in excited state. That's the subtitle I would like to spend some minutes on covering, on teaching you this concept. Chemistry is beautiful. I want serious students, so make sure that you have all the requirements, and you have to make sure that you are ready for learning and not otherwise. This is not entertainment channel. This is official training channel for the serious students from the serious teacher in this material system. So electronic configuration of atoms in excited state. First of all, what does it mean about excited state? When I've been teaching you about the hydrogen spectrum, we found that an atom can be in 3 states. An atom can be at ground state, an atom can be in excited state, an atom can be at infinity regions. So those are the 3 places where electrons can be there. So today, we have been writing the electron configuration when an atom is at the ground state. So everything we'll be discussing after learning the post-exclusion principles, alpha principles, all electronic configuration that we used to write in O level, and even the one that we wrote before, we have been writing for atoms at the ground state. So today, I'm teaching you how we can write electronic configuration at excited state. And I believe that you will enjoy. And that's my intention. So what do you say? So let me give you a little intro. Say that in excited state, the electrons the electrons moves from the lower to the higher, the lower energy level, to the higher energy level. The higher energy level. So as to form more unpaired electrons. As to form more unpaired, say unpaired, more unpaired electrons. As to form more unpaired electrons. Okay? More unpaired electrons. More unpaired orbitals, or to increase the number of orbitals with unpaired electrons. More unpaired orbitals, not electrons. Notice minor correction. More unpaired orbitals. More unpaired orbitals. More unpaired orbitals. Increase the number of orbitals with unpaired electrons at the meaning. So unpaired orbitals, we say that these are the orbitals which contain unpaired electrons. They are singly filled at the meaning. So again, another piece of information is increase the ability of elements to form covalent compounds or covalent bond formation. This process is not involved changing the number of electrons. So we say that this process, or the process of excitation, the process of exciting electrons from ground state, the process of exciting electron from ground state to excited state increases, the advantage increases the ability of an atom so increases an ability, or the ability of an atom to form the covalent bond. increases the tendency of electrons to form covalent chemicals, covalent, we call it covalent compounds, through covalent bond formation. Covalent compounds, we start these compounds and even this type of the bond in topic that we call the chemical bonding, which is the next after this atomic structure. Covalent compounds. Covalent compounds. So the chemical bonding. So the chemical bonding. Okay? So that is the issue that we have to understand. So because we are moving electrons from the ground state to the excited state, then there's another question that we have to ask ourselves. Does excitation, before first excitation, or I write this question, let me remind you how excitation process is taking place in the atom. So consider that you have 3 main energy levels with the Ear principal quantum number. You have 3 to 4 main energy levels. This one is n is equal to 1. This is called Lyman series. N is equal to 2. N is equal to 0. N is equal to 4. So this state is a state that we call ground state. So we have been writing electronic configurations when electrons are in ground state. And then this is state from here going up. Right? Means even if you have another state, you have another state. So all of these from n is equal to 2, we call them, these are excited states. Excited states. So it means when electrons jump from n is equal to 1 to n is equal to 2, that's excitation. When also jump from n is equal to 1 to n is equal to 3, that's excitation. When also electrons jump from n is equal to 1 to n is equal to 4, it has been excited. When electrons jump from n is equal to 1 to n is equal to 4, it has been excited. So these are the excited energy levels and the higher energy levels. Remember that the issue of energy increases as you go up. So energy increase. Right? So we have been writing electronic configurations at ground state. So the issue is, I have to teach you because some of the questions in the final, it means an advanced certificate secondary education, it means final exam, that they used to ask you to write electronic configurations of excited. Means right, maybe for example the questions ask you to write electronic configuration of chlorine at excited state. So you have to understand what does it mean. Otherwise, you can't answer that question. You lose the marks for that question. Right? So good. So this is what going on by the process. We are not discussing about when electrons are returning from excited state to the ground state. No. Our discussion is when electrons is moving from a ground state. When we told that write electronic configurations of this atom, maybe of the atom, say maybe of chromium, or zinc, or radon, or barium, at excited state, means electrons has jumped. First of all, you should know how can you write electronic configuration at a ground state, and then I will show you the electrons which actually will be the first one to be excited in the valence shell, because this process of excitation takes place in the valence shell. Why? Why valence shells, not the inner shells? Why? Do you think why? Why excitation process takes place in valence shells more than inner shells? We call them skull shells. You are not studying. You are not revising the material that I taught you, because I've answered with that question. The answer is because the valence shells experiencing poor or less nuclear attractive force. So it means that just a small amount of ionization energy required to remove electrons from the valence shell compared to nuclear shells, where there's a strong nuclear attractive force between electrons and protons in the nucleus. Keep it. So then this process, the process against the, so she say first of all, number one, so he said that number one, call this number one. This process of exciting electrons from the ground state to the excited state increases ability of an atom to form what? Covalent compounds through the chemical bondings. There's again a second note. We say the process of excitation of electrons. So excitation of electrons. Process of excitation of electrons does not change. So this one does not change. When you say change, it means does not increase or decrease the total number 40, or the number of electrons. Number 4 electrons. But it increases the unpaired or the orbitals with unpaired electrons. It increases the orbitals with unpaired electrons compared to the ground state. With unpaired electrons. So unpaired electrons. So that's what you have to know about excitation of electrons. It does not change. So remember, it does not change the total number of electrons, but increases the orbitals with unpaired electrons. And I will show you what they mean. It means that, for example, you might find if you have the 4s orbital, and then you find that here we have the paired electrons, and then you have another shell here, which is, let's say it is 4p. So 4p is 3 orbitals. Suppose that maybe at the ground state there's only 2 electrons. So when excitation process takes place, these electrons is shifting and coming here, and then start to find it. Now we have this one, and at this point it remains only 1 electrons like this. So you see that now, before it was only 1 orbital, only 1 sublevel which contains unpaired electrons. Now 2 sublevels contains what? Unpaired. So here the number of unpaired electrons increases, and even here. So this is how what's happening. Okay? So you say that the number of electrons of an atom at the ground state is equal to the number of electrons found in the atom at the excited state. That means that there's no any change of what? Number of electrons. So it's a number of electrons in the atom at the ground state is equal to the number of electrons at the excited state. I'm seeing somebody who is not writing while I insist writing. The number of electrons in the excited state. This is equal to the number of electrons, total number of electrons, okay, where? At the ground state, or vice versa true, at the ground state. So this is the sentence I wanted to make. The number of electrons in the excited state is equal to the number of electrons, okay, the number of electrons in the atom, at excited state is equal to the number of electrons in the atom number of electrons in the atom at what? Ground state. So make corrections of those conjunctions or preposition. Add those prepositions. So if that's the case now, we say that, okay, so we don't change the number of electrons, whether to reduce or to increase. We just shift them from one orbital to another orbital. So since exciting of electrons, okay, so we have again a term we call the covalence. Very important because this term is parallel to what I'm teaching you. So I have to teach you a vocabulary called the covalence. Say covalence. You might think that maybe the word covalence is talking about the valence shell. So the question, what is covalence? What is covalence in atomic structure? So I found some of the definition for you. Covalence, as covalence, say covalence again, say covalence again. Covalence, so you say covalence is a process, okay, so no, is a total number, not process, is a total number. Covalence is a total number, say total number. So covalence is a total number. Covalence is the total number of unpaired electrons. Unpaired electrons in the atom. So covalence, say covalence again, this is the total number of unpaired electrons in the atom. So if you have 3 unpaired electrons, means the covalence of that atom will be 3. If you have 4 unpaired electrons, then the total number of that, the covalence of that atom is equal to 2. If you have 4 unpaired electrons, then the covalence of that atom is what? Is 4. So since exciting electrons increase the number of unpaired electrons, so the process is said to increase the covalence. So the excitation process increases what? Increases covalence. These terms are very important because sometimes the questions comes and ask you by using these vocabularies. So you have to understand them and take them serious. So let us do example 5. And this is a little bit concept. Host is teaching you something new. Write the electronic configuration. Write electronic configuration to show the excited state. So excited state of what? Roman 1, aluminium. Roman 2, silicon. Roman 3, phosphorus. So I will solve 2, and then I'll solve for aluminium, phosphorus, silicon will be your homework. Solution. Write electron configuration to show the excited state of, you see? So the key point for this question, the concept, is this two words. Excited state of what? Of aluminium, of silicon, of what? Of phosphorus. Okay? So then it says solution. So the first state, you know that because the aluminium is one of the elements in the 20, in the periodic of 20 elements. So you say that the first state, say that right, the normal advanced electron configuration of what? Of aluminium with 13 electrons at the ground state. So we write at the ground state means that we write the normal electron configuration. Then I will show you how you can use that normal electron configuration to deduce the excited state of that atom. Good. So how do we write? We are allowed to use the noble gases. So we write by using box method. So here it means that by using boxy method. By using box method, because with box method we can show the difference. So you say that this is advanced electronic configuration. Electronic configuration of what? Aluminium at ground state. At ground state. So you know that we need two lines. Electronic configuration of aluminium at ground state. In this one, we say that square bracket, aluminium, and then say what? What the corresponding number gets for aluminium? It's neon. So neon, right? And then if you are using orbital method, neons, then the next is what? 3s square, and then 3p power 1, right? According to the Paul's Offenbach principle. So let me write it clear here. Aluminium, and then this is equal to neon, is equal to neons, which represent the inner shells, and then we have 3s, some label. Here we have, so this is, we fill 2 electrons, pair of electrons, and then we have 3p, but contains only 1 electrons to make 13 electrons of aluminium. But the p sublevel has 3 orbitals. So these electrons is always filled on the first orbital, which is called the px. So listen now. So this is the electron configuration of aluminium at ground state. Listen please. Then now we are going for the second step. We want to excite 1 electrons. Remember that I told you in the previous lecture that 3s and 3p, these are what? Sabu energy level, which is representing what? The valence shell. So the valence shells of aluminium, there's 2 sublevels, 3s and 3p. So we say that again, if you now want to excite, to bring that to promote it, or it means that you just need to give an electron sufficient amount of energy, then something happens. So during excitation, we say that these electrons, the paired electrons, will come here. So this is taking place during what? Excitation, right? Because you have paired electrons. So it's better It's easier for this atom to lose these electrons rather than losing this or the inner. So, if that's the case, you say that, therefore, electronic configuration of what? Of aluminium at excited state now is giving us this, that you have the term configurations of aluminium is equal to what? Neon, and then is equal to what? 3s square, 3p power. So then the s orbital now contains 1 electrons, and then the p orbital, p sublevel, contains 3 orbitals, and has been filled with 2 orbitals. So what happens after that process of excitation? The covalence has increased. The covalence here, we had only 1 unpaired electrons. Listen carefully. We had 1 unpaired electrons. Here you have 3 unpaired electrons. So the paired orbitals with unpaired electrons has increased, as we say. So that's the response for that question. No hassling, no attempt. Then we have a set example for phosphorus. Okay, phosphorus is found in which, what is the atomic or number of electrons in phosphorus? So we have phosphorus, again we have silicon, which is 14, phosphorus is 15, sulfur is 16, chlorine is 17, etc., etc., etc. So the first step, so Roman 3, we say that the electronic configuration of phosphorus at the ground state is this. So we have what? Neon is noble gas, corresponding noble gas. We have 3s square, we have 3p3. So how many? We have total 10. We have 10 there. So listen, this is concept. This is concept. This is conceptual question. So even here, you can write concept. Yes, I wrote concept, fine. The concept is there. Listen carefully. So if we write this electron configuration by using box method, in 3s we have 2 electrons, and also here we have what? We have, remember the Hans rules, half field. So this is at what? At the ground state. So what do you think? If electrons will be excited, where will it be being excited? In S sublevel or P sublevel? Think as a chemist. Huh? Tell me please in the comment sections. Tell me. What do you think? Which electrons is going to be excited here? These 2 paired or this unpaired, and where will it go? Think that you're in an exam and then you find a question like this. What will you do? So, if that's the case, then that's what the concept that I want to share with you. So it means that in phosphorus, so this is the second state, and this is the point where we have the concept. So say phosphorus contains what? Contains what? Contains 2 electrons, 2 electrons in series S sublevel, and they also contain 3 electrons. This is 2 paired electrons. Okay, 3 electrons at 30 at P sublevel. So we say that it's not possible for the secondary electrons in the 3s orbital to move to fill either fill Px or Py or Pz. So it means what happened? It's not possible for electrons to move the pair, one electron, the second electrons in the s orbital, to move from s orbital to the p orbital, because the p orbital is singly filled, contains 3 electrons. So no space here, because these electrons, remember that is negative charging, and even the electrons which are here is also negative charging. So negative and negative repel. So what happens? So you say that for this case, you mean that to write electronic configuration of phosphorus at what? At its ground state, at its excited state. Then we have, in textbook, if they give you this question, they give you the answer, but they don't give you explanation. We have to, so that we have to extend. We have to extend the sublevel from 3P to 3D orbital. So we say that it's true. This is true. So we say that the electron configurations of phosphorus, this is equal to what? Is equal to electron configurations of neon. And then we have what? We have series S square as usual. We have series P cubic. And also we do have, we usually at ground state, we do have also series D, but no electrons to fill. According to what? Paul's exclusion principle. So this is still at the ground state. So if we draw, you find that the series S contains 2 electrons. Then the next, the P contains 3 unpaired electrons, which is in the same. So 1, 2, 3. So this is equal to 3P. And the D orbital is there, but doesn't have any electrons to fill in any orbital. So then, this is the point. So this one, next one, next one, next one. So, if that's the case now, this is an D orbital. So the electron configuration of phosphorus at excited state is this one. So what is happening? The excitation takes place from these second electrons to this D orbital. interesting. So the excited state is given as electron configurations of phosphorus is equal to what? Electron configurations of neon. Then we say that you have 3s, and then you have 3p, and then you have 3d. So here now we have only one unpaired electrons. So you have half filled, half filled, half filled. This 3 sublevel contains how many orbitals? 5 orbitals. So because of the space, I won't show the others. But the electrons will be excited from 3s will be accommodated in this empty orbital. Right? So that's the concept that you have to understand. So this is the response of the question that you've been asked. Good. If you have any question, please don't hesitate yourself. Ask your questions on the comment section. Write the electron configuration sulfur at excited state. At its excited state to show its covalence of 4. This is covalence of 6. So same atom but write in different covalence. Say covalence. You have to understand clearly what the means of covalence. We've discussed it. You have to be careful. Means writing. The meanings of covalence means write the electron configuration. The 4 covalence means 4 unpaired. The 6 covalence means 6 unpaired electrons. So that's what you have to do in this example to enjoy the beauty of chemistry, because chemistry is beautiful.